Okay, good morning. Today, as we discussed yesterday, I plan to solve a couple of problems. One will be from both of them from the makeup assignment, and I have uploaded the solutions for the makeup assignment, and you can go through them, but I wanted specifically to discuss two problems. One is going to be from magnetostatics, and the other will be from transmission lines. The solutions are here in front of you, and I just wanted to go through these problems so I can see what kind of questions you may have. And additionally, I would like to make a few points to keep in mind. I would suggest that all of you read the makeup assignment problems very well, because they provide, there are 10 problems, and they provide a very nice overview of the material that we covered in this class. Granted, not everything. So I would like to ask you to, in addition to going over your homework and solutions, I suggest that you look also at the makeup assignments. One last thing about the final. Your final questions are not going to necessarily be all new. The values may be different, or they will be from problems that we've solved before. But the problems will be very similar to any of the homework problems we have solved so far, or makeup assignment, midterm problems, and so forth. So your highest priority as you prepare for the final will be to go through the problems that we've covered in this class. Make sure you go through my notes. I don't want you to read anything new or beyond that. If you cover well this material, I hope you will do well in the final. And with that, I would like to start here. Okay, so I have the solution for this problem, but this problem practically, it is it's nothing else but a calculation of the EMF voltage, which is called the electromagnetic force voltage. EMF is induced. It's an induced voltage. And what we know is that this EMF voltage is nothing else but a measure of the change of the flux over a given area over time. So the definition for the EMF is the following. If you have a wire, it's a closed wire, obviously, so there is current that can flow through. If you have a closed wire, like and I will draw here so you can see me. If you have a closed wire like this, all right, that's a closed wire. You may or may not have a source. In this one here, you have a source in this one. And the source is a voltage. In the other wire that I gave you, do not have a source. Okay, if now this wire and that encloses a surface, and the surface it encloses is practically in the square, it's the area of the square here, the area of the square, or in fact the best way to do it is just put A for area, A. And this one is the area for the circle. Okay, now if each one of those closed loops is inside a time-varying magnetic field. So if you have a magnetic field that varies with time, then you will have a magnetic flux density that varies with time. Why is that? Because the magnetic flux density is nothing else but mu h. Okay, if you have that obviously the magnetic field lines or the magnetic field that goes through these areas, so you can have magnetic field lines like this that go through this area. All right, also we know that the magnetic field lines also close, they are not open. If you have these and so forth, and these are magnetic field lines. And then in this case, you will have a flux that is practically the integral over the area A of the magnetic flux density. And since it is the integral of an area, the areas we have discussed in the past, a surface is a vector. And why it is a vector? Because it has a direction. What is the direction of this surface? Is the direction which is vertical to the area of the surface. Okay, so now if you take this integral from here, that implies that phi of t, or phi, it's a function of time, phi of t. Okay, and that then implies that there is a derivative of the phi of t with respect to time. And that derivative is not zero, obviously. Okay, so when this happens, then you can conclude that this derivative, the negative rather of this derivative, is nothing else but a voltage which we call the BMF. And this voltage, even if it's not like a battery that you see or like another source that you have placed, this voltage applies on this wire. So the voltage is like placed, is like a battery here that is placed along this wire. And in fact, if you had a battery here placed along this wire, then what would this battery do? It would create a current. Now, I have not given a polarity to this battery, and I have not therefore given a direction to the current, because where the current, how the current flows, which direction the current has to flow, depends a lot on the direction of the magnetic field and how it changes with time. So if your phi of t changes with time so that the magnetic field goes down over time, reduces in magnitude, then the current that is created by the BMF has a direction that opposes this current. So what does that, this change of the magnetic field? What that means is the following. A magnetic field that has this direction here, which I show you, would be created by the right-hand rule from, if I were to find the current that creates this magnetic field, it would have been a current like this. All right? So a current like this would create that direction of the magnetic field, the way I have it. Now, if this magnetic field over time goes down, then the BMF current it will have to have this direction here to be able to strengthen the magnetic field if the magnetic field was going down. And that is what the sign shows here. So in that case, that means that this would be the positive, because if you remember, the electric field, the current from the VMF source comes out of the negative pole. It's opposite to the real current that comes out of the positive pole of the voltage, but of the battery. Now, if the EMF, if the magnetic field increases over time, so then the direction of the current would have been like this to oppose the increase of the magnetic field. And for that current, the direction of the polarity of the VMF would have been this one. Excuse me, the opposite. I need to. Okay, it would have been this one. All right, all of this is happening because of this relationship. Because of the negative, the current has always a direction opposite to so it has a direction, so it creates a magnetic field that opposes the change of the magnetic field we have in place. All right, so again, the electric current or the BMF have a direction, so the current and the BMF a polarity that opposes the change of the magnetic field. So that's what we've learned. Now, let us try to put this in practice. Okay, so we'll solve the problem here. First of all, the first question in the problem is obvious. All right, the question in the problem, the first one, says, and that's why you see it's so simply stated and solved. It says that the two currents, there are two, so it's one loop, and this loop has also a resistor, and the resistor in this loop, it's given to us, it's 10 ohms, and it is a distributed resistance because of losses in the wire, but I have shown it as lumped, all right, so as a lumped resistor to be able to write the circuit equations. In the first case, part one, we have no change in the electric currents, IA and IB, and those are infinite long wires, but they are steady. They do not change with time, which implies that each one of them creates a magnetic field around it, and you find the direction of the magnetic field using the right-hand rule. So I will write here, and then I will write it, and then I will draw it, and then I will probably remove it. But IB creates a magnetic field that looks like this. And this magnetic field goes through the wire. You can see the closed wire. All right, the wire loop, like this. So it goes down, it goes inside the loop, but towards the board. So practically, if I were to show how the magnetic field lines from IB go, they will go like this. Okay? Now we have IA. IA also, so this is IB, and this is IA. IA creates now a magnetic field that looks like this. And looks like that. And also goes through the loop. And as it goes around, it goes like this. It goes like that. Okay, so it comes this way here. And if I were to show how those lines go through the loop, I will show them like this. Okay? So the magnetic field from IB goes towards the board. The magnetic field lines from IA come out of the board. And so the yellow ones go inside the loop towards the board. The blue ones come outside of the loop towards us. And yet, because none of those changes, then none of those creates a voltage on this loop other than the voltage that we already have there. All right, so the only current that in this situation flows through the loop, which is the current I here, it's the result of this voltage V of D. And of course, if you divide V of D by R of D, you get the current that flows, which is 75 milliamps. All right, that's what in this case. Now, we are given in the second case, part 2 of the problem. And let's remember part 2. Part 2 says, is here. And part 2 says that the current IA, the green current wire, is steady. It remains the same as before. But the red current changes versus time as minus 5 e to the minus omega t. And t is time, and omega is given up here. Then everything else is given to us. We have all of the dimensions, right? This D is 1 centimeter. Each of the sides of the loop, this is a square loop, is 2 centimeters and so forth. So we have the area and we have the change that takes place in the current IB. So now we have to solve this problem here, part 2. And in part 2, what do we have? In this case, because the current I sub A does not change, I don't care about the magnetic field that is created by it. So practically, I don't care about this one. And I will erase it. The only field I care about is the one that is created by I of B, which are the yellow lines. And this one, all of this that goes through the loop changes over time. And how that changes, of course, it depends on how the current I of B changes. Now here I write the theory that I expressed before, that I discussed before rather. So this is BMF. And here. So this is the relationship we wrote before. And this is the BMF that is going to be created out of the flux that is due to a wire IB. So I will call it phi of B. And phi of B here. And the flux, as we said before, is going to be the surface integral of the magnetic flux density and over the area of the square, and because the current is producing, this current is producing this field B sub B, then we know from the expression, and that is the critical one to remember, of the field that is produced by an infinite wire. Those expressions, you need to have them available. And the field that is, I will put it here on the side, I will draw it on the side. If you have an infinite wire here, and this has a current, I, and this current produces a magnetic field like this. So according to the right-hand side rule, then the magnetic field is going to have that direction. And this magnetic field, which is going to be along the phi direction in the cylindrical coordinate system, is going to have a value that is going to be I over 2 pi r, where r is this direction. Okay, r. So if you take this, that you need to have those expressions available. They are everywhere. We have used them multiple times, but what I suggest, so when you prepare for your final, write them all on one piece of paper, so you don't have to go quickly through all of these notes that you have, and then you get mixed up with the pages, and sometimes you cannot find it because you're anxious. So write them all on all the formulas you may need to have that you don't remember. Write them on a piece of paper, write them accurately. So check them out, and then use them there. Have them in front of you when you take the exam. So because of this formula, then what we found is this relationship that when the magnetic field goes on the surface of the loop and has this direction here, the one that I show, then is along the minus x direction in the xyz coordinate system, because x is like this. Okay, so as it goes inside the board, has a minus x. And B then, using the formula, is given by this expression here. And therefore, phi is given, or phi is given by this expression, then phi is going to be the flux of this over the surface of the loop. And if we go to the next page, then you find, if you do the integration, that finally this flux has this form. And using this formula for the VMF, you find the VMF. So far, so good. Now, what do we find from 1? Equation 1 tells us that the voltage, or the voltage, the VMF, which is due to, or the magnetic flux density, P, shows that there is a variation of the magnetic field, but the magnetic field goes down over time. So your IMF current here, IMF current, will have to have a direction to strengthen the magnetic field. So it opposes the reduction of the magnetic field over time. So it opposes the reduction of the flux over time. And as the result, the EMF is going to have that direction that you see here. Oops. This one. And you can find the IMF from VMF. If you take the VMF, all right, here, if you take the VMF, yeah, divide the VMF by RD, that is going to give you the IMF current. And you will have to superimpose this IMF the way it shows there. You would have to superimpose it to the current I that flows as we found in the first case, because the current I has nothing to do with IB and IA. The current I only is due to V sub D. So you have found I from part 1, you found IMF from part 2, and then the superposition of the two gives the current that flows through the loop. Okay. Why is it log 3 and not 1? Because let me see, I don't, yeah, it is not a log, it is an ln, but it is because D plus 2 is 3 and D is 1. And is the ratio of the two. So practically, that should be log n of 3. All right. Any questions in the process when we saw about the solution? Any other questions? Any questions about the VMF? Is that a solution? Does this solution make sense? Okay, I will assume yes. So the solution is there. Please check it out. And now we are going to move, as I said, what you need to remember is the following. Make sure that you have all of the formulas available and written for you. And make sure that you don't have to, you solve a problem like that, you understand the direction that IMF takes compared to the magnetic field, the direction of the magnetic field, how you select the direction of IMF. I would normally select it on the basis of that discussion we had about creating the IMF having a direction that creates a magnetic field that opposes the change of our magnetic field, that is the generating magnetic field. And this is going to be the easiest way to find it as opposed to trying to do it mathematically. Okay. We move now to another problem, and that is going to be, let me see. This problem here. So I would like this problem shows the following. It's a transmission line problem. We have a section of a transmission line here. And that has a length which we don't necessarily care. And I would need to ask you why we do not care about this, D1. We have a load at the end, which is 50 ohms. We have then a stub, but the stub is not exactly a stub because it looks like one, but it's a section of a transmission line with a load at the end. And to clarify, we use the name stub for a section of a line that has an open or a short at the end. So an open end section of line is called an open-ended stub, a section of line with a short at the end, which we use to cancel something out is called a short-circuited stub. But a line that has a load at the end is not called a stub. All right, so it looks like one, this one here that I'm drawing. This one looks like a stub, but it's not a stub, it's a section of line. And this line has a load 200 ohms at the end. And then there is this other section of line that has 50 ohms at the end. Now, what I said is we try to find D, so we make the reflection coefficient at A prime to be equal to 0. Now, question, why do we not care about the distance D1? This one. Why do we not care about this distance? Can somebody tell me? Why do I not care? Okay, Ashley says the load normalizes to 1. That's correct. And what does that really mean? When a load normalizes to 1, what does it really tell us? It says what? It says that it's matched. Absolutely. And if it's matched, so David said that. If it's matched, what does that mean in terms of the reflection coefficient? Is 0. Exactly, Cameron said that. And if it's 0, it's 0 everywhere, regardless of how long the line is. So your reflection coefficient is going to be 0 here, 0, is going to be 0 here, is going to be 0 here with respect to Z naught. Okay, so no matter how long you make this line, the reflection coefficient is going to be 0, and so I don't really care about D1. I don't. So I remove it. All right. Now, let's talk about the other transmission line, this one. Why do I care about its length D? Because it's not matched. All right, the line has a load which is 200 ohms, and it's not matched, which means that the reflection coefficient or the input impedance to this line, what do I mean by that? If I look at this line like this, and I see here a Z input to this line, let me call it Z, I put here B prime. So Z input at A prime, B prime, which is practically what I see when I look like this, changes as a function of D. So this one here is a function of D. Okay? So now we want to find D, so we make the reflection coefficient gamma and input equal to 0. All right, so how are we going to think about this? There are some initial observations that you need to make. All right, you should not just draw it. Every problem I give you are usually design problems. We need to make observations. And those observations are important because what it means is will help us simplify the solution. Okay, so let's see. I will stay in this one, the other is too crowded. All right, so let me erase some things to make my observations. We'll make them together. All right, let me now draw here. So we said before this input impedance there, here, which is Z in, B prime is Z naught. Okay, now, as Ashley said before, we are going to normalize things because it's going to be easier. And if we normalize things, normalization makes things easier because it makes the values smaller. So this is going to be 1. Okay, the input there is always 1 because this one is 1. Okay, ZL here is, so let me call that 1, and ZL2 here, normalized, gives us 4. All right. Now let's bring everything to A, B prime, A prime. If we bring everything there, what we see is the following. Then we are going to have an input, make it thicker, an input transmission line there that comes from the left and ends at A prime. And then we are going to have a Z naught here, which is a ZL there is the input here, which is 1. So Z input B prime normalized, which is 1. And there we are going to have Z input at A prime, which is a function of D. And how much do we want to make this one? We want to make the Z input at A prime normalized equal to 1. All right. So practically, we're going to have Z input at A prime normalized equal to, this one is the sum of Z input at B prime plus Z input at A prime. So it's the sum of these two impedances at the end. So these two impedances is the sum. And what we have from there also is, if we replace, we have 1 should be equal to 1 plus Z input at A prime. Oops. Okay, normalized. Which means I find a very interesting relationship, and I find from here that Z input at A prime should be 0. This is very important. So we should find a position D on the line that makes this one equal to 0. That one you have to do up front because this one reduces the complexity of your problem. All right? This is from another problem, the solution. I don't know why I brought it up there. Okay. I think I mixed up somewhere when I was writing the solutions yesterday. Is it this one? No. Let me see. 1 second. Bear with me. I think I moved the circles. That one's different. There it is. Okay. So that is, I'm sorry, I moved the yesterday. I will rearrange them. I moved the plots. But let me go back to our problem. So I had solved it. Can put this one up here. Okay, so now we have this. Then what do we do here is we write the expression for this one, for z input of a prime, and try to make it equal to 0. So we'll insert this one. And so we have z input at a prime, b prime, a prime, b prime. Okay, the z input at a prime, b prime, normalized, will be equal to ZL2 plus J tangent. And I think we called that D, beta D, over 1 plus J ZL2 tangent of beta D. All right, and then from here, we have to make that 0, which means we need to make the ZL2 equal to J tangent beta D. Okay, what is ZL2 is 4. 4 equals J tangent beta D. What does that tell you? That tells you that you can never, because tangent is always a real value, has always a real value, that tells you should the second box you drew be the Z input A? Let me see. A prime, B prime, A prime, B prime, B prime, A prime, B prime. Okay, corrected that. So we see from here that there is no, okay, that takes, we saw from here that, we see from here that there is no D that can make ZL2 equal to 0. So what is the next then? We can only here minimize as the solution, as it says here. We cannot make it 0, but you have to find this smallest number, the minimum that makes this, the minimum value for Z input at A prime, B prime that makes this gamma equal to 0. And so the best way to do this would be by bringing here the Smith chart. All right, it's very difficult to do a minimization of a function like this to find, so for example, to find what is the minimum value. You can do it. I mean, the minimum value, so you would have to find the derivative of this with respect to D and to make that equal to 0. But it's very complex. I will not suggest that. The easiest way to do this will be to find a, I'll tell you what will be the easiest way. The easiest way will be to find the lowest real value for Z input lowest real value for Z in A prime B prime, okay? And so the lowest real value for this, and that implies that we need to find the lowest possible real value, because if it's not real with the complex numbers, it goes, it can become very large, having an imaginary part as well. So ZL, let's see how we're going to find this, how we're going to think about that. You can see it on the Smith chart, but we will think here from what we know. We know that if you have a line like this one, let me go back to our line here. In this line that we have here, I will highlight it. The load at the end is 4. Now, that's a real value of input impedance is the load. If you move at a distance d, which is half a wavelength, how much is going to be the Z input at A prime, B prime? If lambda is half a wavelength, can you tell me how much is going to be Z input at A prime, B prime? Normalized. How much is it going to be? If the load normalized is 4, how much is it going to be, is the input impedance at A prime, B prime, B? Normalized, it's 4. If a lambda over 4, a lambda over 2 away, half a wavelength away, how much is it going to be? It's going to remain the same. Do you remember what we said? That if you move by half wavelengths, an integer number, no, it's 4. And on this line that I have highlighted, the normalized load is 4. So if I go at a distance d, so to A prime, B prime, if I make D to be half a wavelength, my input impedance at A prime, B prime is going to remain 4. That's a very large number. Okay, so 4. If I go by a quarter of a wavelength, how much is it going to be? So we don't like half wavelengths. We don't like a half wavelength. We don't like a wavelength and a half. All of these are not good because it's going to give me 4. What if I move from by D, which is a quarter of a wavelength? How much is your Z input at A prime, B prime, B? Is it not going to be the inverse? So when D is lambda over 4, then your Z input at A prime, B prime is what? 1 over ZL2. Remember that? Exactly. So it's going to be 0.25. Okay, that's a very small number. So practically, if I make D to be lambda over 4, then my Z input at A prime, B prime takes its lowest value, which is 0.25. Okay, and in fact, it's like here. You see that? So practically, if that happens, then the Z input at A prime, excuse me, B prime, all right, becomes 12.5 ohms. And that's the lowest real value, which in fact, if you use the Smith chart, and then you write your load of 200, normalized 200 ohms, which is 4, and then write the constant VSWR circle. Then you're going to find that the lowest real value for Z input at A prime, B prime is 12.5 ohms. And if you use this value here, so the total input impedance at A prime, total input impedance at A prime becomes then 62.5 ohms. And the reflection coefficient for that is 0.1, which makes a very nice VSWR. So the reflection coefficient becomes very small, and therefore the VSWR becomes very small. So that is, in fact, how you would solve a problem like this. But I would say the solution for this problem is like here, all right? Practically, this is the most important observations that you would like to make ahead of time to be able to solve the problem. Okay, now that was another example that I wanted to solve today to remind you how to solve these problems. So I will reload. Don't copy down the solutions for the makeup because I had mixed up the order of those slides. I will fix the order of those slides because I had put behind this problem the slides from another problem. And then I will add the new things. I will use the ones that I have here. I will make a PDF out of this PowerPoint and I will upload it again. And so remember what I said. First of all, I have office hours today and I will have office hours tomorrow from 12 to 2. And I would encourage you to join for office hours if you have any questions. Read these problem solutions, read your homework solutions. I have uploaded homework 11 and I will upload it homework 12 today. You have all of those available. Just look at them, know what we've solved, and you're gonna have no problems in the final because the final is gonna be any one of these problems. I promise you right now, it's not gonna be a new problem. I will pick any of these problems that we have already solved, but I will change the values. So read, know where your solutions are, and then come prepared to the final on Thursday from 10 to 12. I'm gonna have a Zoom for that. I don't wanna see all of you. I will be on Zoom in case you have any questions. I will try to see how you do break rooms for your teams. If I be successful with that, then I will inform you by email that you can use the breakout rooms and for your teams to do the team part, the team final, the group final. And as I said, both finals will be available at both, everything is gonna be available like we normally do for a final. Everything is gonna be available at 10, but the guidance will be to use 1 hour for the individual and then 1 hour following the individual for the team. You would have to solve the individual to be able to solve the team homework. And then I'm not suggesting that you will have to solve it accurately. I'm not gonna base the questions of the team on the solutions of the individual, but you will need to have gone through the individual to familiarize yourselves with the problem. And then I will be on Zoom in case you have any questions, but I will try to help you with the breakout rooms so your teams can talk to each other. So with that, that's where I am. And then if you have any questions, let me know, come and join me in office hours. And so good luck with your studies. Take care. Bye.